Now we formally define big O, big omega, big theta, little o, and little omega. Okay, so let us define them in such a way. I try to define them in such a way that you can easily visualize the differences between all of them. Okay, so the assumptions and the variables and the definitions I've written at the top. Okay, so the first is that let Fn and Gn be functions that map positive integers to positive real numbers. Okay, positive integers to positive real numbers. Okay, so Fn and Gn are two such functions. Now assume a few constants. There are two constants specifically, a real constant c greater than 0 and an integer constant n0 greater than or equal to 1. n0 is determining the input size. Okay, it's a basic minimum input size. So there are two constants. There are two functions Fn and Gn. They map positive integers to positive real numbers, and two constants c greater than 0 and n0 greater than or equal to 1. Now why we say that Fn and Gn are positive, mapping in positive to positive in the positive domain? Because for asymptotic analysis the functions has to be asymptotically positive. That means for sufficiently large n they should produce positive values. Okay, so that's why asymptotic analysis needs positive functions. Okay, so now we say Fn is big O of Gn, or Fn belongs to the set of functions which are of the of the same growth rate as Gn. That's why the set notation. With the presence of this constant c and n0, such that Fn is less than equal to c times Gn for every n greater than equal to n0. Okay, so now what does it mean? I have a graph. Let me draw another graph just to explain that part, then it will be clear for you. Suppose this is a graph. Okay, what we say, Fn is big O of Gn such that Fn such that there exists a real constant c greater than 0 and integer constant n0 greater than or equal to 1, such that Fn is less than or equal to c times Gn for every n greater than or equal to n0. Okay, so this n is an integer. Okay, n is an integer always. Okay, so now you see, what does it mean? Suppose this is Fn. Okay, so this is a function that maps positive integers to positive real numbers. Now I'm saying, what is the growth rate of Gn here? So Fn has to be less than or equal to c times Gn for every n greater than or equal to n0. Now let's assume this is this is the c times Gn. Okay, so let's make. Okay, so this is Gn. Okay, and this Fn is less than or equal to c times Gn for every constant n greater than or equal to n0. So now this is the position where n equal to n0. Okay, so Gn will overcome Fn. Gn will act as an upper bound to Fn for the input size n equal to n0. We say that for the sufficiently large input size, Gn will eventually act as an upper bound of Fn, or Fn will eventually beat Gn. Okay, so this is the idea. This exactly same graph we have drawn here. So this is Fn, the black line. You can see that the red line is big O of n, and this position where they cross is the n0 for this case. Okay, big O case. You see, above that, big O of n will always, forever act as an upper bound. It will never ever come back below this black line. Okay, that's the idea. Fn is upper bounded, Fn less than equal to c times gn for every integer n greater than equal to n0. So this is the thing, like I said earlier, like 2n squared less than 5n squared. It's something like that, okay? Or you can say 2n squared, 2n cubed less than 5n to the power 4, okay? It will never ever be less than. Initially it might be, but you know, suppose this is like n equal to 1, then it's 2 times 1, okay? 1 cube, that is 2, and this is 5 times 1 to the power 4, that is 5, okay? So 2 less than 5. Initially it can even happen that this is, you know, less than this because of some constants, but finally eventually for a certain value of n which is sufficiently large, Fn will always beat Gn. That's the idea of big O, okay? Now you see little o, I just wrote below that to show you they are almost exactly same, okay? So Fn is small o or little o of Gn, G of n actually I should say, or Fn belongs to the set of functions which have, you know, similar growth rate as Gn, such that Fn is less than c times Gn for every n greater than equal to n0. See, this is the loose upper bound, okay? Loose upper bound means suppose it is pretty high, okay? Consider here it's very high, it's not a as tight as the big O, okay? This also may not be the perfectly tight, can even have tighter one, but still this is, the red one is much tighter than the little o, okay? So this is like I said, suppose it's 2n squared is the Fn, so this suppose 5n to the power 5. This is little o because it's so large, that's definitely it's bounded, but we can definitely have a tighter bound like a red one or big O, okay? Now you see the big omega, like big O was giving the umbrella upper bound, big omega will give the umbrella lower bound, okay? So everything is same, only is that Fn greater than equal to c times Gn for certain n greater than equal to n0. So let's see this big omega, okay, the blue line. You see here Fn is the black line. Here initially big omega was kind of winning. Now, but finally after certain time, after this value, this is n0 here, the blue line, the omega line comes below Fn. After that the blue line will never go above black line, because for all n greater than equal to n0, this is n0 where the lines cross, Fn is greater than equal to c times Gn. So big omega serves as a lower bound to Fn. And just on the same line, Fn is small omega of Gn, like little o's concept, Fn is greater than c times Gn. So this is a much lower bound. Omega, capital omega or big omega was a tighter lower bound to Fn, but small omega is a very loose lower bound. So this is the n0 for that. Okay, so I hope you understood what is the significance of n0, that after that n0 whatever relation exists will exist, it will never change. So now so that means big O is something like less than equal to, okay? It gives you the upper bound. If you cannot remember upper bound or lower bound, remember, think it as a big rock. You're trying to push it from the mountain and it will kind of slide down by itself. So this, you will remember that this is high to low, okay? So this is the upper bound, upper. That is easy. If you remember this as upper bound, then no problem in remembering big omega as the lower bound, okay? Big omega is the lower bound. So that's why Fn is bigger than that, okay? Here, because this is the upper bound, Fn is less than that. And then what is theta? Okay, before I say that, so I mean this is like analogy, okay? Big omega is less than equal to big omega is greater than equal to big O is less than equal to, so small o is just less than, small omega is just less than. Then what about theta? I say that theta is equal to, okay, this is like, consider a sandwich, okay, you have one bread, put some peanut butter on it, so that's serving as a lower bound, that's like the small omega, okay. Then you take another bread and you put some peanut butter or jam on it and you put over the previous bread, okay, that's serving as the upper bound, big O, and whatever remains in between this layer of peanut butter and jelly is the Fn, okay, so that's in between, so that has to make sure that they have both the upper bound and the lower bound. That's why Fn equal to theta of Gn, or Fn belongs to the set of functions of the same growth rate as Gn, if and only if, sometimes if and only if is written as IFF, if Fn belongs to big O of Gn and Fn belongs to big omega of Gn. You have to make sure you are both upper bound and lower bound, then only you see this area of n, you see this, at this stage it is both upper bound and lower bound. Lower bound was satisfied already here, you can consider it's n01 or something, but here it is like n02, okay. So this is the place where this is both upper bound and lower bound, so that means here Fn is big theta of n. Fn was already big O of n, big omega of n from here, okay, but Fn is big O of n from here, so Fn is big theta of n after this point, okay. So that's why we also can say theta of Gn equal to big O of Gn intersection big omega of Gn, both the values intersection, and then you will get the theta of Gn. Okay, so now so that's why we say theta is like equal to, big O is the upper bound, big omega is the lower bound, when both the bounds are satisfied we have like equal to, okay, then it's called theta. So that's why we have small o which is like less than, small omega which is greater than, we cannot have a small theta, because for equal to you cannot have a like this, you know, it's less than equal to less than, greater than equal to greater than. So for equal you cannot have anything, that's why we do not have any small theta, okay, remember that. So here let's see some example. 2n square equal to big O of n cube, okay. So or 2n square belongs to the set of functions with similar growth rate as n cube. Now if you want a tighter bound, then you can even, you know, go tighter, adjust the constants, so you can even have 2n square equal to big O of n square, as long as you adjust the constants here. That's the constant c times n square, okay, remember c, you have to make sure it's definitely greater than, have to be greater than 2, even if it's 2.1 still that's okay, it has to be more than 2. So that is the tightest bound you can have, okay, but this is also a generally tight bound because this is better than big O of probably n to the power 4, okay, this is tighter than that, so this is not considered small o. You can also write 2n square equal to small o of you know, n cube or something like that, that's also possible. Now another is root n equal to big omega of log n, okay. So what does it mean? It means up to a constant factor, that's the c, you know, root n is at least log n for sufficiently large n. So that's the way of reading it, okay. So what's the way of reading it? Root n equal to big omega of log n means log n is a function which is binding root n from the bottom, okay. So it's a lower bound, if you remember omega is the lower bound, okay. So that means up to a constant factor root is at least log n for sufficiently large n. So after that root n is, you know, much higher than log n. Okay, so I hope you got a good idea from these graphs and the definitions. So I have tried to, you know, color code them in such a way so it's easy for you to understand, and give some examples. Make sure you read the book to understand what are the other possibilities, other kind of relationships which is important for asymptotic analysis, and you will understand better from there also.